Good afternoon, everyone. I'd like to thank you all for joining us today in our continuing education series. Today we'll be presenting the second half of fiber optic system design. My name is Jessica Petrohoy, and I'm the marketing coordinator at fiberoptic.com. Fiberoptic.com is a leading provider of fiber optic products, training, and rental equipment, and we are pleased to present this topic to you today. The key to good design is in the questions you ask. Some of the items we discussed last month include planning a network, operational requirements, fiber types, physical and environmental requirements, inside plant routing, and outside plant routing. In today's part 2 of the fiber optic system design webinar, we will be discussing choosing components, calculating a power budget, testing and documentation, preliminary cost estimates, and practical considerations. With us today to talk about system design is Terry Power. Terry is one of our senior instructors and a field technician with over 25 years in managing and testing networks. When Terry is finished, we will take questions from the GoToWebinar question box at the bottom of the screen. Remember that our webinar series are recorded and they're available to you online at fiberoptic.com/webinar. Today's webinar will be available for on-demand viewing within about a week. So thank you again for joining us today. And at this time, I turn the presentation over to Terry.
And good afternoon, everybody. Again, this is Terry Power. As Jessica said, I've been doing communication electronics for a lot of years. For those of you who have not attended any of the webinars, I'll give you a brief bio. I started doing cable television work in 1987. After working on electronic warfare systems in the Air Force. I started with coax as fiber started really growing up in the cable TV industry. I moved more and more over into the fiber realm. By 2007, I was outside plant coordinator for Tele Barbados, working and living in Barbados. I was sent to fiberoptic.com for certifications and met the president of the company here when I moved back to North America in 2009. He put me on staff, and I have been here since in a variety of capacities, from running crews in the field, doing testing in stomping through the jungles of Panama, working in Guatemala City, been to Haiti a couple of times, as well as training through the Middle East and into Africa. So anyway, so today we're going to finish up our conversation we started last month about fiber optic system design. And there we go. So last month we talked about choosing component. We're going to talk this month about a brief recap from last month. We're going to talk about choosing components. We're going to talk about calculating a power budget, testing and documentation, preliminary cost estimates, and then we're going to wrap up with some practical considerations. So last month we discussed planning the network, operational requirements. We talked about different fiber types, not just single mode or multi-mode, but we dug in a little bit and talked about different types of each. We talked about physical and environmental requirements, inside plant routing and outside plant routing. Now we're going to jump into choosing components. And we need to look at the transmission equipment. Transmitters, are we going to use multi-mode? We've got multi-mode as well as single-mode options. Multi-mode is going to be either a light-emitting diode, LED. That's going to give us an overfilled launch condition. It's going to be relatively low power, short distance, low speed. We're going to be under 622 megabits. But it is significantly less expensive. It is obviously the least expensive way to go if it meets your operational requirements. Now, the vertical cavity surface emitting laser which is not really a true laser, and that's another webinar presentation by itself. But it has a restricted launch condition. And what it does is it's got a very tight beam. It's kind of like an LED on steroids. And it will give a somewhat higher power as opposed to an LED at negative 20 dBm. VCSEL is going to be somewhere around 1 dBm. It will go into the gigahertz bandwidths, and you're going to need to use OM3 or OM4 fiber, the laser optimized multi-mode fibers. Now, for single mode, we've got a couple of different laser options. We're going to talk about the Fabry-Perot laser. It has a fairly wide spectral width, about 4 nanometers wide. It's capable of up to 10 gig of modulation or bandwidth. It can only be used for digital transmission. It will not handle analog. And it is not, it says on the slide, not temperature sensitive. More appropriately, it's not extremely temperature sensitive. Any light source is going to be, to a certain degree, temperature sensitive, and even a Fabry-Perot laser will burn up if you don't control the temperature in its environment. Now, the much higher cost is going to be your distributed feedback laser. Now, this is going to give you several benefits. It's got a very narrow spectral width, typically 1 nanometer, and if you're working with DWDM types of options, you're going to need the narrower bandwidth, or narrower spectral width rather, so that you can pack the channels in as closely as possible. It is capable of the data modulation up to or greater than 10 gig. It can be used for both analog and digital. It is, again, specifically used for dense wavelength division multiplexing applications, and it is extremely temperature sensitive and requires good air conditioning in the environment where it is used. Now, receivers. We're going to be looking at the most common type of receiver is going to be the PNP, or the positive intrinsic negative diode. It is, again, the most common, has a very low power requirement. It is inexpensive, but it's limited in sensitivity. Not just in its low end, but in its high end. It's easier to overdrive and saturate these types of receivers, these photodiodes. It can be used for analog as well as digital systems, and in fact it is the only detector that can be used for analog. The avalanche photodiodes are normally only used with single mode. There's a fairly high cost and circuit complexity. So the whole cost of the thing goes up. Produces gain. It amplifies the photocurrent by 10 to 50 times. So what you're getting is a preamp, and then the receiver, and then another amplification. It's multi-stage. That's the complexity of the circuit. It cannot be used with analog systems, and it is very sensitive to its ambient temperature. Again, air conditioning is going to be needed in the environment where it is used. Now, amplifiers. There are a couple of different options for amplification. The semiconductor optical amplifier, or OSA, is laser device. It operates at either 1310 or 1550. It is a direct amplification up to about 12 dB, and it is bidirectional. Now, the erbium doped fiber amp, or EDFA, is your higher power. In fact, you can see you get some optical amplification up to 35 dB. So you can get some screaming outputs from this. It's certainly not a class 1 laser. It uses a pump laser to excite the erbium doped fiber. That operates typically at 980 nanometers. The whole thing will operate within the C-band, and it is used almost exclusively with DWDM to extend the range of these multiplexed signals. Now, of course, we've got passive optical devices, wavelength division multiplexing, add-drop multiplexers, optical switches. We could also talk about passive optical networks or splitters. But with the wavelength division multiplexing, we're basically doing like a channel combiner in the old coax world. We get these, all the different wavelengths, we pack them together with a combiner onto a single piece of glass. Optical switches will allow us to redirect information or to talk to an entire network using a fiber optic link rather than the old copper Cat5 or Cat6 links. And then add-drop multiplexers allow us to take discrete lambdas off, add some back on. Perhaps we've got in the middle of our run, we want to take off a one wavelength and feed it to a customer. We can take that off and then we can add their signal back in to continue flow down the line. So, cable designs. Now we've talked about the hardware components, but now let's talk about how we connect the dots. We've got different types of cable designs. We're talking about how we bundle up the individual fibers. Our indoor cables, as you can see from the top two drawings, are going to be our distribution, breakout, and cord. Now the upper left-hand picture is distribution cable. It is multiple tight buffered fibers surrounded by aramid yarn and an outer jacket. It's the least expensive of the indoor cabling. It doesn't have a whole lot of extra fluff. It's just tight buffered fibers, aramid yarn, and an overall jacket. If you go higher than 12 count, it will start using a colored streamer to bundle the individual groups of fiber into the equivalent of buffer tubes so that you know which blue fiber is 1 or 13 or 25. You can go to some fairly large counts. It's the lightest weight of all of the two primary indoor cables, and the easiest to pull and operate. Now I'm going to jump to the bottom of that and talk about cordage. Now cords are just one individual tight buffered fiber with aramid yarn and a jacket. And the reason I jump to the bottom is when we talk about breakout cable, which is the picture on the upper right hand side, if that looks like a bunch of individual patch cords all bundled together with a strength member and an outer jacket, you would be correct. So breakout cable is individual simplex cords bundled together. Now this gives you benefits when you're terminating, because if you're going from, say, a patch panel on one side of the room to a patch panel on the other side of the room or maybe in the next room, and you want to be able to directly tip your jumpers between them, this gives you the option of basically bundling up all of your patch cords, and instead of having 24 patch cords running from room to room, you can have one breakout cable, and terminate that on both ends and have all of the strength and protective capabilities of the individual patch cords just bundled up into a neat package. Now for outdoor cable, we're going to be looking at loose tube, loose buffered cable. We can look at stranded or unitube, and then armor is going to be one of the possible options on either of these. So stranded is going to be our traditional loose tube gel filled with a buffer tube, colored buffer tube, so that we know which blue fiber is 1, 13, 25, etc. And inside that buffer tube is going to be some kind of water blocking compound, whether it's the dry block powder that gels up when it hits moisture, or if it's the old icky pick or water resistant gel. Now unitube, the picture on the lower right somewhat looks like unitube. What it's trying to show there is a ribbon fiber. And ribbon fibers are typically run in a unitube construction. I have seen some very large count ribbons run in something more like a stranded, where they would have colored buffer tubes, but the buffer tubes would of course be substantially larger. Unitube construction is what you'll see with the fiber counts with ribbon, 144s, even 288s I've seen all bundled in one unitube. Now armor on the outside. That lower right picture, you can also see the armor just under the jacket. That is an option with loose tube buffered as well, stranded. This is necessary only when you have rodent chew issues or direct bury, where you're going to be concerned about crushing forces. If you do not have those two issues, you really don't need the extra weight, expense, or frankly opportunity for bloodletting that accompanies working with armored cable. Getting a nice clean break on the armor is a skill set unto itself, and most people that work with armor that I've ever worked with usually bled when they were working with armor, because it breaks off jagged and will be very sharp and carve up your hands. Been there, done that. So if you don't need the armor, I would avoid it. But if you do have squirrel chew, rat chew, I was teaching a class over in Kuwait back in March. And of course they don't have squirrels, but they do have rats that get into their huts, where they do their switching and amplification. And so they're very concerned about using armored cable to protect against the rats that get in there and chew on the cables. So it's not just squirrels, but any kind of rodent that will chew on the cable. You want to protect your cable and your fibers inside the cable by using armor. If you're going to direct bury, you want to give yourself a little extra protection against crushing forces. If you're underground and in conduit, I wouldn't worry too much about armor. All right, termination. Excuse me. We're going to be looking here, are we going to use our existing system terminations, the existing connectors? Is this going to be, are the connector types going to be driven by the transmission equipment? Are we going to have plugs that are specifically needing to have LC connectors? Are we going to have angled connectors? What exactly are we going to have? Some of the termination options would be the ST, used mostly in multi-mode. It's one of the older styles. It's a bayonet plug, kind of stud it and twist. The most common in the 90s and early 2000s was the SC, or subscriber connector. Now, small rectangular connector with a key on it. Both the ST and the SC are the standard 2.5 millimeter ferrules, and you can get them in UPC or ultra physical contact, or an angled polish connector. Then you've got the LCs. Most SFPs and XFPs today use a duplex LC connector. It's the small form factor connector, uses a 1.25 millimeter ferrule, and the slide here says it's most common now. I'd say it's probably about 50-50 with SC, but it is becoming a much more common connector for no other reason than density. If you've got a limited amount of rack space, a limited area for your cabinet, the smaller connector, you can get 2 LCs in the space of 1 SC. So there's a great deal of capacity difference by using the LCs, and since so many of the SFPs and XFPs use that smaller form factor to limit their footprint and make smaller cabinets or smaller boxes, the LC is becoming much more popular in the fiber world. Some of the other termination options, the old FC connector. There's still some of them out there, and I've gone out on a couple of testing jobs where I still saw FC connectors out in the field. And those are the ones that are threaded all the way, and they look like a coax connector in a lot of ways. And I'm thinking that probably F came from the old F connectors. It was a single mode connector used primarily in the telecoms world. And then you've got the MPO, or multi-fiber push-on. This can have everything from 2 to 12 fibers all terminated into one block. It's used mostly in data centers and will allow you to plug in. We had some stuff in Barbados where we would plug an MPO on one side that would catch all 12 fibers, and then we could run those to individual receivers or individual transmitters, and obviously with the transmitters it would all be on a combiner. All of this running into the 12 fibers on a combiner, and then with the other end we would be receiving 12, sending it to receivers. MPOs are also getting a lot of play with fiber to the home, because you can pre-connectorize a drop and make it quicker and faster for an installer to go out in the field. They won't need splicing equipment. They can just go out with X, Y, and Z drop cables and pull in the appropriate cable and plug it in on both ends, and the install is done. So we're starting to see a whole lot more of the MPOs in that environment as well. Okay, so calculating a power budget. A couple of calculations that we're going to talk about, but first we're going to talk about, we're going to basically total up all of our losses. So let's look at what some of them might be. Our fiber loss. Now remember, fiber loss is the only loss characteristic in our design that is wavelength dependent. Different wavelengths have different amount of losses per kilometer, so that attenuation per kilometer is going to be different at 1310 or 1550, 1625, or any of the discrete lambdas that you might use with DWDM. And then we're going to have to look at our OTDR testing results to determine the loss and attenuation over the fiber. Other anticipated losses: splitter or coupler losses, OADM, that's our add drop multiplexers, wavelength division multiplexers. All of these are going to have losses as we put stuff together, and when we receive it, we're going to have more loss. And of course, attenuators. And we may find that our design is going to call for us to have attenuators. Worked on a small little network a little bit south of here, and we were running the lowest power SFPs we could get our hands on, and we still had to put in attenuators because we were overdriving them on the other end, because they wanted to run with single mode fiber in anticipation of the future growth. So we ran single mode fiber, but it was so efficient in its transmission that we had to calculate attenuators into our plan. So these are all the things that you want to take into account when you're looking at your anticipated losses. We want to throw in a safety margin. How many restoration splices might we need? Span length changes due to restorations. And that's usually, well, it could be if you've got slack out in the field and it's accessible. You might lose some of your fiber length by cutting out a bad part and using retrievable slack in the field. Or it may be that you go out and you have a whole section ripped down and you add additional fiber with some slack, and so you may add fiber to the length or add length to the fiber itself during a restoration. So you want to account for all of this in your safety margin, you also, or restoration margin. You also want to look at your aging margin, temperature fluctuations of the equipment, aging and degradation of the fiber. Now, theoretically, the fiber should last 40 to 70 years in the field if it's properly installed and you don't go tinkering with anything. The outside plant fiber should last for 40 to 70 years. Inside plant would be about the same, but you're going to be changing out technology before that 40 years is up anyway. Receiver dynamic range, we're going to need to know this. We're going to need to know the lowest level at which your receiver can discern data reliably. And that's going to be published by the manufacturer. You'll find that on all of the specification sheets. And again, if you're using a very high power laser, or if you've got very short distances, you may need to use a attenuator to knock down the signal a little bit and stay out of the overdrive range. Because while it says dynamic range, and we think mostly on long runs about how low can we see, that dynamic range has an upper end as well. And if you push harder than the upper end, it's going to saturate the receiver. And just like looking into a pair of headlights in the dark, it's going to saturate and you won't be able to discern ones and zeros. So both of these need to be taken into account in design. Splice losses and connector losses. Now, in both of these, we have to look at how are we going to design. As Jessica said in her introduction, fiber optic design is more about asking the right questions than having all the answers. And in this case, we've got some questions to ask. Are we going to base our power budget off of max allowable losses according to the standards? Or are we going to look at company best practice? Are we going to specify a max allowable loss for a splice or a connector that is less than what EIA, TIA, or ITU specs allow for? And the difference could be pretty substantial. I mean, we normally expect a .05 loss for a splice, but the standards allow us to have up to .1. And that's a pretty substantial difference over 20 splices. You're looking at maybe 10 dB of difference in your design. So how are you going to design? Are you going to design for the worst possible case with the industry standards? Or are you going to look at real numbers and base it off what you can expect from best practices? And in both of these cases, those numbers could be pretty substantially different. And if you're trying to save money, you're of course going to look at best practices, but then you're going to have to put in a larger safety margin and larger restoration margin to account for changes in the field. If, on the other hand, you design for the worst case, it to a certain degree gives you a built-in additional safety margin that will allow you to continue and operate the plant for years to come. So you've got to weigh cost. If you design for the worst case, then you're going to have shorter runs, more often, more equipment, more amplifiers, more everything. If you try to stretch it out a little bit further by going according to best practices, it doesn't give you as much wiggle room for stuff to happen. So these are the questions you have to ask when you're even beginning the design to figure out what way you want to do the numbers. Now let's put all of that together and let's look at, say we've got an existing link and we want to see what the max allowable loss would be across that link. So we're going to look at our fiber attenuation times the number of kilometers. We're going to look at our splice attenuation loss for fusion splices. We're going to look at fiber attenuation or splice losses for mechanical splices. I generally expect about a 0.3 as the max allowable for a mechanical splice and 0.1 for a fusion splice. Connector attenuation. Are we going to look at ITU standards, which only allows 0.5, or are we going to look at EIA-TIA standards, which allows all the way up to 0.75 dB of loss at a mated pair of connectors? I generally never see connectors that bad, but technically, according to EIA-TIA standards, you could have a 0.75 connector pair still pass the standards. And then you're going to put in whatever safety or operational margin you want to put in. And so that's how you find the total loss across an existing fiber. Now, if we want to look at our link margin, if we look at our transmitter power and we look at the receiver sensitivity, the lowest signal, we can see and discern data. Take the difference of the two, and that's going to give us how much loss we can have between that transmitter and that receiver, and the link still work. Then we have to look at our link margin, all of the things we talked about on the previous slide, our fiber, our splice losses, our connector losses, other anticipated losses, everything we can think of, and a safety margin. And we're going to total up our link margin. If that link margin is less than the power budget based on transmit power and receiver sensitivity, then the link should work. If that link margin is greater than the power budget, then the system will never function. So we have to then start looking at different options, ways that we can either go to a wavelength with less loss. Maybe we were looking at operating at 1310 because 1310 is cheaper. But then we realized maybe we need to go to 1550 to get that extra range, because the loss for 1550 in the cable is going to be about 0.22, whereas with 1310 we're going to be about 0.35. And that doesn't sound like a lot of difference until you get out to, say, 10 kilometers. Then we're looking at 22 dB of loss, or 2.2 dB of loss, or 3.5. Suddenly those numbers start sounding a little bit further apart. And we go out to 50, and then we're looking at 11 dB versus 70. No, I did the math on that wrong. Yeah, 35. No, that's still wrong. I'm often. Jessica's over here laughing at me. 17 or something thereabouts. You get the idea. The numbers get bigger and further apart the further we go. So we're going to have to look at some of our options for wavelengths. Okay. So now let's talk about testing and documentation. And I do want to remind everybody that we do have the question box at the bottom of the screen. And as soon as we finish up with the presentation, we're going to take questions. So you can go ahead and type in your questions as you think of them. Maybe we'll get the answer while we're talking, and if not, then we'll address those questions at the end of the presentation. So talking about testing and documentation. We're going to primarily talk about single mode fiber here. Field testing of a single mode, we're going to look at the optical loss test set and the optical time domain reflectometer. We're going to talk about advantages and limitations. I don't like the word disadvantages. We're going to talk about limitations. Each does something very important and very specific. And each does something that the other cannot do. So yeah, there's limits to what each piece of equipment can do, but they're not disadvantages. It's simply understanding the equipment you're operating. Pre and post installation, final acceptance, optical loss testing, documentation, troubleshooting. The different types of testing here, when you're building out a system, you want to look at measuring the loss and double checking the received fiber meets the ordered specs. Your final acceptance is going to be all of your fiber, all of your OTDR shots that you keep for reference. Your optical loss testing is going to be all of your final loss characteristics for each link. And documentation, you're going to want to keep up with every piece of paper, because you go out to do restoration later, you want to know what loss you're supposed to have so that you know what it is you're testing. If I go out and hit a link and I've got, it goes 15 kilometers and I've got this amount of loss, my documentation will tell me if that goes the right distance, if it's too much loss, too little loss, what's going on with the link. So, optical loss test set, power meter and light source, and the OTDR are the two most important tests. Again, pre-installation when the fiber arrives on site, post-installation. This is where we verify our fusion splices, all the construction. We typically do this including 1625 so that we can see if there's any macro bends. We can correct everything, redo, do our reburns. There's going to be reburns. It's not a failing, it's simply part of the process. So once we get all of that done, then we take our final acceptance tests. This is where we save the traces. We do our loss per kilometer, our total distance testing. Everything is done at this point. Then we might want to do periodic testing just to see if anything has changed out in the field. In Barbados, I found a couple of problems developing where people were messing with the cable. We shared a manhole in several locations with the power company, and the power guys were messing with the cable at a splice location and causing some macro bends by doing periodic additional testing. I saw that there was a problem developing, got out in the field, found out what it was, addressed it with the power company, and alleviated a possible outage later. So these are the kind of tests that you want to look at in your design, what you're going to specify during the design, and if you're going to be the operator later, you want to look at all of this. And all of these forms, all of these traces, all of this information should become part of the permanent record for whoever the end user is, because this is going to allow us to know what we're supposed to have when we're out testing and troubleshooting. It's the benchmark. It's the best the cable's ever going to look. And that's when we want to save those traces as our benchmark. Some other test equipment that we might be wanting to specify as we do our design. We might want to look at polarization mode dispersion. We might want to look at chromatic dispersion. We want to look at, those are primarily our limiting factors for distance. I used to teach in class that there was no practical limit to the bandwidth on a single mode fiber. And that has recently, well, not recently, but with the rise of and discovery of polarization mode dispersion and it coming to the forefront, we have realized that that's the limiting factor. PMD is going to cause us to either shorten our runs or limit our bandwidth over our existing distances, because it's just going to cause so much delay that the signal breaks up. Chromatic dispersion is pretty much under control. We can handle that. We can use compensation coils or compensation modules. We want to measure it sometimes to make sure that we match up with engineering, but it's linear, it's engineerable. You can get the amount of dispersion per wavelength from the manufacturer of the fiber when you're purchasing it. If you're doing DWDM or CWDM, you might want a spectrum analyzer where you can look at your individual fiber channels. And then protocol testing devices. Some places I've worked really love these, and some say if it passes CD and PMD and all of my losses, then the fiber is going to work. But you can get bit error tests, you can get sonic simulators, several kind of protocol testing devices that you may find useful or your engineering company may want. Now, the optical loss budget we're talking about here, it's done at the beginning of the design. I usually go for worst case scenario, allowed component losses as opposed to the standards in the real world. And again, you may need attenuator to bring power back down into the dynamic range. All of these are areas we've discussed already. We're going to look at total span loss, including all of our connectors, splices, fiber loss, any other components. We should always test at 2 wavelengths. When we're doing our loss testing, we want to look at the wavelength we're going to operate and at least one higher. And I generally like, when I'm having people to test their construction and turn in traces or loss characteristics to verify what they've done, I like 1625 being reported, because if there's a macro bend or anything bad in the construction, that's going to show up as excessive loss at 1625. So a lot of people are operating at 1550 now and then asking for 1625 as the additional wavelength. And then you can compare all of this measured losses to your loss budget and determine if attenuators are required or if it's going to meet the specs and the standards needed to operate the design. Now, the OTDR is used to get a picture of the fiber span, whereas a power meter and light source measures power. And it is, for that reason, the most accurate device for determining loss. The OTDR is the most accurate piece of equipment for telling you where it is. So you can look at a calculated loss on an OTDR, and it will usually be fairly close to measured power with an optical loss test set. But it's not going to be, totally as accurate for loss. What an OTDR does for us that nothing else does, it gives us distance. It tells us how far away the components, whether it's a splice connector or whatever, how far away is it? And again, using a dual wavelength, I can compare my losses, and by looking at 1550 and 1625, I can see any differences in the two and determine if there's any stresses, macro bends, or anything like that in the construction. And so as a designer, I want to specify those tests and see those traces from the contractor to verify the construction was done to my standards. Because as we're designers, we're the ones that are setting the standards and the specs that we're going to be asking the technicians and installers to meet. We've already talked about dispersion testing. One of the platforms that's very good at using these modules is pictured here, the FTB 500, and it's a multi-module platform that will allow us to have PMD and CD modules, which are pretty big and will not fit in most of the handheld equipment. I've already mentioned dispersion compensating fiber. Has a high negative dispersion at around 1310, which allows us to do pulse shaping. NZDS cable has a lambda 0 or 0 dispersion point that makes it very good for DWDM and long haul. Depending on your wavelength, it's either going to be slightly positive or slightly negative chromatic dispersion, but it is designed specifically for long haul operations and works mainly in the C-band. And then you've got an option of regeneration, where the signal is received, it's processed, it's cleaned up, our timing pulses are regenerated. It's then put back into a transmitter, and a very new, clean signal is started over. And this allows us to reshape the pulse, do any retiming. And this is going to have to be done every a few hundred kilometers, even with amplifiers. We want to go ahead and receive it and make sure we get everything cleaned up. So let's look at some primary or preliminary cost estimates. Higher bandwidth requirements, higher equipment cost. The longer the wavelength, the higher the equipment cost. Okay, we might want to go with 1550 because we can go further, but the equipment is going to cost more. So we've got to weigh out whether we want to go back to 1310 at the lower cost. The more complex the transmission scheme. CWDM is complex enough. You go to DWDM, you're going to use the lower spectral width lasers, your prices are going to start going up. You start using add-drop multiplexers, your cost goes up again. You start using programmable add-drop multiplexers, and you got another layer of cost. So again, the more complicated your transmission scheme, the higher the equipment cost is going to be. And where do your equipment costs come in? Okay, we can think about the components, but we also got to think about panels and racks. Where are we going to put the components? Splice enclosures and hubs out in the field, cable management devices, installation How much are we going to have to pay per meter for the installation? Are we going to do it ourselves, or are we going to have equipment rental? Working with a design right now that we're going to end up going out and having to rent a cable caddy because the equipment that is available in-house will not hold the size reel that the fiber is going to come on. So now we're scrambling around to rent a cable caddy. That's got to be factored into your cost. Fiber termination and splicing. You know, after we build this upcoming project, then somebody's got to come back and put all the pieces together. All of that has to be factored into your costs. Testing. After it's all put together, we're still going to have people test it and verify. So we've got to certify those test results. What standards are we going to use? Contract the testing out, or are we going to do it in-house? There's a difference in cost there, obviously. Are we going to purchase our own test equipment? Now, a lot of people with a power meter light source and an OTDR, purchasing is a good thing. You start getting into limited use items like PMD and CD modules, well, you know, purchasing those to use them 2 or 3 times is probably not practical. We're talking $75,000. That's one of those situations where you either want to rent the equipment or you want to hire an outside tester. Now, one of the things that we do here is we own all of that equipment, and we have our testers come out and do the work. You pay for the testing, and you get the report, and then everybody goes their separate ways, and you have no additional cost. That's typically what I see more and more of, and that was the kind of work that I've done down into Central America, was testing work just like that. And then you've got to look at the timeline to do the testing. How long are you going to be out in front of it? All of that's going to factor into your cost estimates. All right, we're going to wrap up in just a minute. Again, I do want to remind you that we have the question box at the bottom of the screen, and you can go ahead and put in your questions, and we will address those right after we finish this last section and in the presentation. Now, practical considerations. Now, these are just some of the things you want to ask yourself at the beginning of your project. As you even begin to think about, maybe I want to do this, start asking these questions. How many fibers am I going to run? However many fibers I think I need, I typically try to multiply it times 4. If I think I need 12 fibers, and I'm really going to use all 12, then I'll probably pull a 48 count. If I think I'm going to need 144, I probably pull a 288 or 436. I don't want to get caught without fiber. Well, it says here, future proofing. How long before you will need to upgrade? Designed for 25 years rather than 5 years. And some have even suggested 75-year lifespan on fiber. Look at it this way. With the inside fiber, I've got some actual numbers. The Building Industry Consulting Services International, or BICSI, estimates the life expectancy of a commercial building to be somewhere around 70 to 75 years. They expect the life expectancy of the technology is 5 to 7 years. So within 5 to 7 years of right now, everything we have, the technology will be obsolete, and we will be into something completely new and different. How many fibers am I going to need tomorrow? How many fibers am I going to need in 5 years? How many am I going to need in 25 years? And if I can get a 75-year life expectancy on outside plant fiber, how many fibers are my grandchildren going to need? These are the questions you want to ask. Understand it is way cheaper to pull larger fiber counts once than it is to go out and pull multiple fiber counts, because the installation cost of the labor is more significant than the cost per meter of the fiber itself. You want to identify your projects, or products rather. Start with your specification lists. All numbers will need to have some sort of test method to verify them. So if I say I'm going to want this amount of loss on the overall span, I'm going to want this much per splice, this much per connector, I need to specify how I want that reported and tested. That's all part of what we as designers are responsible for doing. Talk to at least 4 vendors and component manufacturers. Don't go to the first guy and he sells you some beautiful thing, some beautiful story, send some really attractive salesperson to you, and you end up buying the first thing that anybody talks about, and then you find out from 3 other people later that that's probably not the best course of action, or it's experimental and you've just become a test subject. So ask around. Talk to at least 4 people. Get with people that know more about the system than yourself. Don't get too too full of your own knowledge. Find somebody that knows more and bounce ideas off of them. You want to resolve any of the conflicting facts, and I use that term loosely. People are going to tell you a lot of stories, and you've got to resolve where those conflict. Know the cost impact of your decisions. We already talked about that. Change to a higher wavelength, add cost. Change to from CWDM to DWM, add cost. So all of these factors have to be taken into account. Then you choose your products. So I want to thank everybody for being with us today. I'm now going to take a look at the question box and see, what about zip cords? Now, when I refer to a zip cord, I'm referring to a duplex patch cord. And that's going to be basically like the old lamp cords, where you had the 2 conductors and you could zip them apart. They had the little piece of the outer jacket holding the 2 together. What I refer to as zip cords is a duplex patch cord, and it's 2 individual cords that have that piece of the jacket material holding them together. And I don't know why they call it zip cords, because I can't zip them back together, but they are designed so that they can be pulled apart, but it's used in duplex applications. When I was talking about the SPFs and XPFs and the duplex LC, that's the type of cord that you would be using. Now let's see, have a client who wants 2 spans of a single mode to be the same length. I'm not certain of the type of end equipment. What would you consider why a client would need links? I'm not quite sure what we're asking here. 2 different routes, but he wants them to be the same length. That could be because of the latency. we worked on a project doing a lot of testing on a link that was running between Chicago and New York City. And it turns out that the link was designed to run between the Mercantile Exchange in Chicago and the Stock Exchange in New York. At every hut where they did the regeneration, and they had a place where they could add and drop customers, every fiber ended up being exactly the same length. So if I had a patch panel that was close to the input, they used longer cords than the ones that were further away, so that the amount of time it took for the signal to travel on any fiber was identical to any other fiber. Because a matter of milliseconds can make the difference in profit or loss in the stock exchange, particularly with some of these big numbers. It could be substantial. The price could change by a few pennies in the milliseconds, and as soon as that happens, you've hit the button. If the price changes before the signal arrives, it could cost you a tremendous amount of money. So this link was specifically designed so that every fiber had exactly the same length and would take exactly the same time to arrive. So I don't know if that exactly answers your question, but it's something that I've had experience with that kind of goes to what you were saying. And please, if you've got follow-up questions, put those in. Now, I've got a question about IOLM software from Exfo on OTDRs. I like Exfo equipment. Anybody that's talked to me knows that. I don't know. IOLM is, for me, it was, Now, I'm old enough to remember working with computers that had DOS. And when they came out with Windows, I thought Windows was for people that couldn't handle DOS. Because, you know, I could do DOS. Now, over time, Windows became much more integrated and is actually an operating system now rather than writing on top of it. But in the beginning, my thoughts about Windows were much like my thoughts about IOLM. If you can read an OTDR trace, I don't need the machine to do it for me. We're working on a project right now that the IOLM software is struggling because we're splicing on patch cords, and it's not able to separate the loss of a splice that is, say, 4 or 5 meters away from the connector. And it all gets lumped together, and it's causing us a tremendous amount of difficulty. Now, I can set up my OTDR on these short runs to a pretty small pulse width and distinguish between the two. I can see them. I can separate them. The IOLM software can only do so much. You know, it's like an elementary school student reading that OTDR trace for me. You give it a certain number of parameters, and it's going to give you back whatever analysis you tell it to do. It's still limited. It's certainly not artificial intelligence. And it will certainly never replace the eye of a trained technician. So, is it better than nothing? Yeah. But I don't think it will ever replace a trained technician. Not at least in my lifetime, not at least until they can get true artificial intelligence into a small box that you can carry to the field. Let's see, I'm going to wait for just another moment or two to see if we get a couple more questions. I will remind you that if you have additional or follow-up questions, or if you are listening to this presentation in our video archives, you can send questions to training@fiberoptic.com. And some member of the staff will respond. Very often it will be me, but there are going to be times when other people may be better to answer the question. You can also contact us if you have questions about equipment and prices. You can also contact sales@fiberoptic.com and get additional information there about costing on test equipment or anything like that. So, again, I want to thank everyone for being with us today. We know that your time is valuable, and you chose to spend an hour and some change with us today, and we're honored. Thank you very much, and again, if you have any questions, make sure to send them to training@fiberoptic.com and look for the on-demand video about a week from today, and that will be at www.fiberoptic.com/webinar. Thanks a lot and have a great afternoon.